Hey guys, so today we're going to go over Unit 6, lesson 3. There are a lot of questions on this lesson, and so I want to help get you through all of the ones that are kind of like application based and that may be a little bit harder. And so I'm going to go through all of that with you in this video today. But just to get started, this lesson is on acids and bases. And so I kind of wanted to give you an understanding of what are we even doing this for and what are we doing? Why am I having to learn this? And so if you think about what these things have in common, coffee, lemon juice, tomato juice, these are actually all acids. They're all acidic. They may not be very, very strong, but they have some acidity to them. Acids are things that generally taste sour. They turn litmus paper red. If you do a little test strip of litmus paper, it'll turn it like a pinkish color. They are corrosive to metal. So if you put them in with some metal, then they will break it down. They generally donate a proton to the other reactant, or they accept a pair of electrons. Acids are kind of defined in different ways. The general definition is that an acid is something that has the ability to donate a proton, or it has an ability to accept a pair of electrons. And we'll talk about that in a minute. And then when you think of what these things have in common, this is salt water, oven cleaner, and baking soda. These are all bases. Bases taste bitter. They turn litmus paper blue. They're slippery. So think of like soap. Soap is a base and soap tastes bitter, right? They dissolve organic compounds like soap. Soap can help you dissolve organic compounds and fats so that it can get off your skin. And bases are opposite. They accept a proton from the other reactant, or in other words, they donate a pair of electrons, or that's another way to define them. And so I just kind of wanted to give you a glimpse of that. And the pH scale has to do with it, right? That range, as you get higher, it becomes more basic. So when there's a pH of 7, it means that it's neutral. But anything besides 7, if it's above 7, it's going to be basic. If it's below 7, it's going to be acidic. And so, yeah, I just kind of wanted to give you a glimpse of what an acid and base is before we jump into like all the nitty gritty details. There are 3 different ways to define an acid and to define a base. The first way is with something called an Arrhenius acid. Arrhenius acid. Arrhenius acids are defined by increasing the H plus concentration. That bracket means concentration in the solution. Okay. So an acid is something that increases H plus. So when you look at this scenario here, let's just figure out what the acid is here. So here we had HCl and H2O. And then on the other side, now we have Cl negative and H3O. So if I look at the HCl right here, what happened to my HCl? Well, it must have donated or it basically gave that H over to this one, right? Because now it's just Cl negative, and this is not H2O anymore, it's H3O. So you can see that the HCl gave its H plus away. It gave its H plus away, which is why the water now has an H3O rather than H2O, because the water accepted it. So the HCl increased the H plus concentration in the solution, right? And so we know that that is going to be the acid in this scenario. For the next scenario here, which one increased it? Well, the H2O became H3O, right? So that means that the CH3COOH, it gave away this H. When you look here, see how that H is missing? It gave away that H. And so this is the acid in that scenario here. And then as far as a base, an Arrhenius base is something that typically increases the OH negative concentration in the solution. And so NaOH would be a base because it has OH, and then as a product, it like released it. And so an Arrhenius base is something that releases OH negative. An Arrhenius acid is something that releases or gives away H plus. So we'll do examples now in the actual problem itself. Let me just erase all of my scratch work here. Okay, so let's see. This is slide number. I got lost on my slides here. Okay, here we go. Slide number 10. So this is problem number 10 in your lesson. Okay, so this is problem number 10. It says, which equation demonstrates a strong Arrhenius acid? Well, I see two that are an Arrhenius acid because anytime I see H3O plus, I know, oh, that means that H plus was given to it. Like here it was water and now it's H3O plus. And so this could be this could be our answer because it is an Arrhenius acid because Arrhenius acids increase H plus. And so when you see H3O plus, you can think, okay, that could possibly be an Arrhenius acid. This one also has H3O plus in it. And so these are both Arrhenius acids. They both increased H plus in the solution. But which one is a strong, keyword strong Arrhenius acid? So in order to do that, I have a list. It's in your student resource folder. It's in like the other folder. It says like other resources of strong acids and bases. So here's a list of those strong acids and bases, and we can compare that to what we have. So for our strong acids and bases, here they are here. When you look at what we have here, this is a potential acid and this is a potential acid. Because remember, they are donating to that H3O plus. You can see because now it's just H1CO3. It gave it away. So that's the acid. Here, this is an acid because it also gave it away and became a Br negative. So is H2CO3 a strong acid or is HBr a strong acid? Okay, HBr is a strong acid. And so that is going to be our answer here. So the answer, I'm going to circle it in red, is actually C for HBr. It's a strong acid. Number 4, which one demonstrates a weak Arrhenius acid? That would be this equation right here. Here is our weak Arrhenius acid. It still donated H+. You can tell because it was H2CO3 over here. And over here, it's now just H1CO3. So it donated H+. But it's not a strong acid from that strong acid list. And so A is our weak acid. Which equation demonstrates a strong Arrhenius base? Remember that Arrhenius bases are things that donate OH, which is called hydroxide. You should memorize it. This is called hydroxide. Okay, so which one of these have hydroxide in them? Which equation here? Y'all look and see. Which one has hydroxide in it? This one does, right? This has LiOH on this side, lithium hydroxide, and then it breaks it down. And so this is a strong, and let's double check that that's strong. So it should be on our strong list. And look at that, LiOH is on our strong base list right there. And so we know that that is a strong Arrhenius base. Okay, next question, number 13. Which equation demonstrates a weak Arrhenius base? This one was an Arrhenius base because it had hydroxide in it. Do any of the other equations have hydroxide in it? Well, this one does on this side. You see how this has hydroxide? And so the H2O in this situation like broke off and became OH negative on this side. And so this one also is an Arrhenius. The H2O in this scenario is the Arrhenius base. And we know that because we know that this is an Arrhenius situation because it has OH negative in it. And we know that it's a weak one because it's not on that strong list. But it's the H2O in this situation because it went from H2O on one side and then it broke off that H and it became just OH negative. And one of those H's went like with the other one. So, yes, it went with the other one. It became C5H5 to C6H6. So it like donated an H there. And so this is our weak base. The answer is D here, not B, because that's a strong base. Okay, so that's Arrhenius acids and bases. Arrhenius acids donate H+. Arrhenius bases donate OH negative, okay? The next type of acid is called Bronsted-Lowry. A Bronsted-Lowry is kind of similar. The acid is defined as something that donates H+, and the base is defined as something that accepts H+. So let's look at this example here. So if we have, let's follow this trail. So see how we have HCl on this side? And then on this side, we have Cl negative. So for that to have happened, HCl must have donated H+, right? Because it's like the before and the after. right? So do you see how it donated H plus? And now let's look at the NH3. NH3 went to NH4 positive, so it accepted H plus. This is called a Bronsted-Lowry acid and base. It's kind of similar to Arrhenius, except that the base is defined a little bit differently. It's defined as accepting H plus. So let's look at some examples of this in action from your lesson. So for number 21, it says, in this equation, which substance is a Bronsted-Lowry base? So going back to our definition of a Bronsted-Lowry base, a base is something that can accept H plus, okay? A base is something that can accepts H plus. This is confusing here. Again, the reason I'm going through these is because these are kind of confusing. But for this scenario here, LiOH breaks apart, right? And when we ask which substance has the ability to accept H plus, it would be something that would have a negative charge. Like in the future, could it accept H plus? And so they should have said which substance is a conjugate Bronsted-Lowry base, like that. Because it's something that's going to be on this side. Conjugates are on the right-hand side. And in this scenario, it's going to be the OH negative because it has the ability to accept H plus. It has that negative charge. It's going to want to accept an H plus in the future. Nothing else here has the ability to accept H plus. LiOH does not want to accept H plus. Li plus does also not want to accept H plus. Next question. In this equation, which substance is the stronger Bronsted-Lowry acid? Again, I don't know why they said stronger here, as if I think maybe you could look at a chart in your lesson as well, but I would have said which is the Bronsted-Lowry acid. So remember, acids are things that donate H plus. So which thing here donated H plus? Let's just circle one of them and look at what happened to it. So when you look at this scenario here, what happened? Did it donate or accept H plus? Well, in this scenario, you can see that the H is missing. And so it donated in that process of the before and after, it donated H plus. So it is the Bronsted-Lowry acid, the CH3COOH. So in this question here, it says, which substance is the strong Bronsted-Lowry base? The H2SO4 donates a hydrogen. So it is, right there, when you look at that, it is the acid. And when you look at our list, H2SO4 is a strong acid, right? H2SO4 is a strong acid. So I'm going to write that down, that it is a strong acid, okay? And when you look at the water, what happened to the water? The water became H3O. It accepted an H because it went from H2O to H3O, right? So it is the base. And even though water is not on our strong base list, because the acid is strong, I think we're going to treat the water as if it's also strong. They kind of match each other on strength. So the H2SO4 is strong, therefore the water is going to be strong. And so H2O is the strong Bronsted-Lowry base in this scenario here. Okay, in this equation here, number 24, which substance is the stronger Bronsted-Lowry base? So earlier, we're kind of flipping back and forth. If you remember, this was the acid, okay? And so which one's going to be the base? The base is going to be the thing that accepts H plus, which is the NH3. So for number 24, the answer is NH3, okay? Last type of acid and base is a Lewis acid and a Lewis base. And a Lewis acid is something that accepts a pair of electrons, okay? And a base is something that donates a pair of electrons. So in general, you will be given this, I think even on your quiz as a hint, okay? The H plus is going to be the acid because it has the ability, it's a positive charge, right? And so it's going to want to accept some electrons to neutralize that H plus. So what happens is the water actually looks like this. I drew out the water. Water has these extra electrons right here, and they come out and like attack the H. And so the H accepts those electrons and the O donates them. And so generally the H plus is the acid, the water is the base, and it forms a complex called H3O plus. So in this scenario here, which substance is a Lewis acid? It's the H plus, because it is something that accepts a pair of electrons. It's going to be something with a positive charge. The Lewis acid will be something with a positive charge because it's something that accepts a pair of electrons. Which substances, and this is a multiple choice thing, you can choose multiple. Which substances are a Lewis base? Water is going to be a Lewis base because, like we said, water has the ability to, remember that a Lewis base is something that donates electrons. Water has these extra electrons that reach out and offer them to the H plus. NO3 negative also has that negative charge, so it also has the potential to donate electrons. So the NO3 and the water have the potential to be bases in this scenario. So both of those would be correct. They both can donate electrons. And then lastly, which is the acid-base complex? It's always going to be the H3O plus. That is going to be your complex for the purpose of these lessons. So hopefully that helps a little bit. Honestly, I feel like this lesson is pretty in-depth, and so don't feel overwhelmed about it. Just know not all of chemistry is going to be this difficult. And the reason I'm going through this with you is because I know that these questions are difficult. And so keep up the good work, keep asking questions, and don't get overwhelmed. Just come text me or join my classroom, or if there's a substitute teacher, if I'm on maternity leave, just check in with them and have them help you out, and keep pestering them and keep asking questions because you deserve it. And so I hope that you ask the questions and understand it for yourself. Have a great day.